Welcome to Podcast Learn and Fun.
Yeah, so today we are talking about something that I think is super interesting.
Oh, yeah, for sure.
Quantum entanglement.
Okay, so.
One of the things that I think is interesting to point out is in the quantum world, things don't quite behave as we expect them to in our everyday experience.
Yeah, I mean, like we think that objects have, definite properties.
Right. A ball is in a specific location.
Exactly.
In quantum world, things can exist in multiple states at the same time.
So it's like a coin spinning in the air.
Exactly.
Before it lands, it's both heads and tails at the same time.
That's exactly right. That's what we call a superposition.
So it's kind of like the universe is playing a game of maybe with reality.
Yeah, and this maybe-madeness becomes even weirder when we start talking about multiple particles.
Yeah, because it's not just one coin in the air now, it's two coins.
Exactly. Imagine two coins inextricably linked.
Oh, wow.
So that knowing the state of one instantly tells you the state of the other, no matter how far apart they are.
And that's essentially entanglement.
That's the essence of entanglement.
That's where it starts to get really strange for me, at least.
Yeah.
Because if they're linked and you know one, you instantly know the other, even if they're really far apart. That's like faster than the speed of light.
Right, and that's the puzzle that has baffled physicists for decades.
Yeah, I can imagine.
This spooky action at a distance, as Einstein called it, challenges our fundamental understanding of space and time.
So is everything we know about physics wrong?
No, not entirely, but we need a new framework to understand them in the quantum realm.
Okay.
And that's where this concept of Hilbert space comes in.
Okay, Hilbert space.
Yeah, imagine a vast multidimensional space where every possible state of a quantum system can be represented as a point.
Okay, so it's kind of like using coordinates on a map
Exactly.
to pinpoint a location, but instead of, latitude and longitude, we're dealing with all the possible properties of a quantum particle.
Right, you got it.
So is it like Hilbert space is a map of all the maybes?
Exactly. And when we have multiple particles, their Hilbert spaces get combined in a way that allows for entanglement. It's like merging two maps into one.
Okay, I can see that.
Creating these new possibilities for how they can be interconnected.
So how would we actually describe this in the Hilbert space?
We use something called a tensor product.
A tensor product?
Yeah, it's a mathematical way of combining the individual Hilbert spaces of each particle. Think of it like weaving together two separate threads to create a new, more complex pattern.
So it's not just an addition of the two spaces, but like a connection that reflects the entanglement.
Precisely. And within this combined Hilbert space, we can have states where the particles maintain their independence.
Okay.
These are called separable states, or states where they are intertwined, and we call those entangled states.
Okay, so let's talk about those two a little bit more.
Sure.
What makes separable states different from entangled states?
So in a separable state, it's as if the particles are just chilling next to each other. They're individual states, independent and unaffected by each other. Think of two dancers performing their own routines on opposite sides of the stage.
Okay, so they're together but separate.
Right.
Okay, now the entangled states sound much more interesting.
Yeah, entangled states are where the quantum weirdness kicks in. Here, the particles are no longer independent actors, but part of a tightly choreographed duet. Their states intertwined in a way that defies our classical intuition. Measuring the state of one particle instantly reveals the state of the other, no matter how far apart they are.
So it's like they're connected by an invisible thread, sharing information across these vast distances.
That's a great analogy.
And it makes entangled states seem so fascinating and so powerful.
Right.
But to really see it in action, maybe we could use an example.
Yeah, let's take a simple example. Two qubits.
Two qubits.
Think of them as the quantum equivalent of bits in a computer.
Okay.
But instead of being either 0 or 1, they can be in a superposition of both.
Okay, so they're both 0 and 1 at the same time.
Right. And what happens when we try to measure one of them?
Yeah, what happens?
That's where the magic happens.
Okay.
When you measure one qubit, you force it to choose a definite state, either 0 or 1.
Okay.
And at that very moment, the other entangled qubit instantly knows what state it needs to be in, even if they're light years apart.
So it's like the measurement of one sends a signal to the other.
It's as if it does.
And it collapses that superposition.
Exactly.
Yeah.
It reveals their correlated states.
So they really are part of this cosmic dance.
Exactly.
Perfectly synchronized, even across these huge distances.
And this interconnectedness is what makes entanglement so powerful and potentially revolutionary for technologies like quantum computing and communication. But to fully grasp those possibilities, we need to dive a little deeper into the math that describes entanglement exploring tools like the Bell state, which helps us quantify just how intertwined these particles are.
Okay, so let's explore this Bell state and see what other mind-bending things are waiting for us in the quantum realm.
The Bell state is a specific type of entangled state for two qubits that perfectly encapsulates this inseparability. It's a mathematical expression that shows how the two qubits are intertwined in a way that cannot be factored into individual states. They are truly a single entity, their fates intertwined.
So they become more than the sum of their parts.
Precisely.
Right.
And this Bell state is not just a mathematical curiosity, it's the foundation for many experiments that have proven the non-local nature of entanglement, showing that this spooky action is not just a theoretical concept, but a real phenomenon that challenges our fundamental understanding of reality.
Wow, okay.
Yeah.
So that's really amazing to think about, and
It is.
we'll have to leave it there for now, but next time we'll talk about even more mind-blowing stuff.
Absolutely. We'll dive deeper into those next time.
Sounds good.
So one of the most fascinating things about this Bell state is that it can't be broken down into individual states for each qubit.
Yeah.
It's like trying to separate two sides of a coin. They're fundamentally inseparable.
Okay, I see. So that kind of highlights the difference between classical correlations and quantum entanglement.
Right. In the classical world, we're used to correlations of things that happen together.
Like thunder and lightning.
Exactly. But those events still have separate causes.
Okay, so how is that different from entanglement?
Imagine two gloves,
Okay,
one right placed in separate boxes.
okay.
You pick a box at random and find a right glove. Immediately, the other box contains the left glove.
Okay, yeah.
That's a classical correlation. The gloves were always a pair, even when separated.
So even though we didn't know which glove was in which box until we opened one, the outcome was predetermined.
Right.
But with entanglement, it's like the particles are deciding their states at the moment of measurement in coordination with each other.
Exactly. With entanglement, it's not just about hidden information. It's about the particles being in this fuzzy, indeterminate state until the act of measurement forces them to make a choice. And they always make that choice together. And this brings us to the mind-blowing concept of non-locality.
Okay, non-locality.
Yeah.
What is that?
It's the idea that entangled particles, no matter how far apart, are connected in a way that transcends space and time. When you measure one, it instantly affects the state of the other, regardless of the distance between them.
Wait, so they're communicating faster than the speed of light.
Right, it seems that way.
But Einstein said that's impossible.
Right, Einstein himself was deeply troubled by the implications of entanglement, calling it spooky action at a distance.
But it doesn't actually violate the principles of relativity.
Not necessarily.
Okay, I don't really understand how that works.
The key is that the information shared between entangled particles is not the kind of information that can be used to send a message or signal faster than light. It's more about correlations about a shared fate, rather than a direct communication channel.
Okay, so they're not sending each other secret messages.
Right. They're part of a cosmic dance, but they're not communicating in the traditional sense.
Okay, so to test this non-locality, they came up with this Bell test.
Exactly.
How does that work?
The Bell test involves creating entangled particles, separating them by a significant distance, and then performing measurements on them independently. The results of these measurements, when compared, show correlations that cannot be explained by any classical theory. It's like flipping two coins that are magically linked, always landing on opposite sides no matter how far apart they are flipped.
Oh, wow. So it's ruling out any possibility of hidden instructions.
Yeah.
It confirms that the particles are making their choices together instantly across any distance.
Precisely.
That's pretty amazing.
It is. And this realization opened up a whole new world of possibilities for harnessing entanglement for practical applications, particularly in the field of quantum computing.
Quantum computing.
Yeah, that's where it gets really exciting.
Everyone's talking about quantum computers as the next big leap in technology.
Right.
So how does entanglement fit into all of this?
Entanglement is at the heart of what makes quantum computers so powerful. In a classical computer, information is stored in bits, which can be either 0 or 1. But in a quantum computer, we use qubits, which, thanks to superposition, can be both 0 and 1 at the same time.
Right, we talk about that.
And here's the key. By entangling these qubits, we can create a network of interconnected quantum states, allowing them to work together in a fundamentally different way than classical bits.
So we're not just increasing the amount of information we can store.
No, it's about the complexity
It's about the complexity.
of the calculations we can perform.
Okay.
Yeah.
So it's like instead of having to try each path one at a time, we can explore all possible paths simultaneously.
Exact. Like trying to find the best route out of a maze.
Okay.
A classical computer would have to try each path one at a time.
Yeah.
But a quantum computer, with its entangled qubits,
Yeah.
could explore all possible paths simultaneously, finding the solution much faster.
Okay, so we're talking about a whole new level of computational power here.
Yeah, think about applications in medicine materials, science, artificial intelligence. It's like we're on the verge of a technological revolution,
Yeah.
driven by this bizarre and beautiful phenomenon of entanglement.
That is mind-blowing.
It is, and the potential of entanglement doesn't stop there.
So there's more.
It's also being explored for secure communication through quantum cryptography.
Quantum cryptography.
Yeah, which utilizes the unique properties of entanglement to create unbreakable encryption keys.
Okay, so how does that work?
Imagine you want to send a secret message to a friend. In traditional cryptography, you'd use a secret key to encrypt the message, and your friend would use the same key to decrypt it.
Yeah.
But the problem is if someone intercepts that key, they can read your message.
So it all hinges on keeping that key hidden.
Right, and that's not always easy.
Not at all.
But with quantum cryptography, we can use entangled particles to generate and share a secret key in a way that's fundamentally secure. Here's how it works. We create pairs of entangled photons, sending one photon from each pair to the sender and the other photon to the receiver. Because these photons are entangled, their properties are correlated even when separated.
So they're like two halves of a secret code.
Exactly.
And measuring them reveals the same information to both the sender and the receiver.
That's the idea, and the beauty of this is that any attempt to intercept or eavesdrop on these photons would disrupt their entanglement, immediately alerting both the sender and the receiver that something is wrong.
So it's like an alarm system built into the communication channel.
Yeah, it's like using the laws of physics themselves to protect our secrets.
Wow, that's really incredible.
It is, and this is just one example of how entanglement is being explored for applications that were once thought to be impossible. From unbreakable codes to ultra-fast computers, entanglement is opening up a world of possibilities that are still being uncovered. But to truly grasp the potential of this phenomenon, we need to dive a bit deeper into how we measure and quantify entanglement, moving beyond just two entangled particles to systems with multiple particles and increasingly complex states.
Okay, so let's unravel these complexities of multi-particle entanglement.
Okay.
See what other surprises are waiting for us in this world of interconnectedness and spooky action.
All right, the world of multi-particle entanglement is where things get even weirder and more exciting. Instead of just two particles dancing together, imagine a whole ensemble, their fates intertwined in a complex choreography of quantum states.
So it's like upgrading from a duet to like a full-blown symphony of entanglement.
Exactly, and to navigate this complexity, we need new mathematical tools and concepts. For example, instead of just the Bell state, which describes the entanglement of two qubits, we need to consider generalized entangled states that can represent the interconnectedness of 3, 4, or even hundreds of particles.
But how do we describe these entangled systems?
One way is to use a concept called the reduced density matrix. Think of it as a way of focusing on a specific part of the entangled system while still accounting for the influence of all the other entangled particles.
So we're zooming in on a specific section, but still recognizing that every thread is connected to the overall pattern.
Exactly, and this reduced density matrix allows us to quantify the entanglement of individual particles within the larger system, giving us a measure of how strongly they are correlated with the rest.
So we can still isolate and analyze the relationships between particles even within this complex web.
Precisely. And as we explore these multi-particle entangled systems, we're discovering new and fascinating phenomena, like entanglement swapping, where the entanglement between two particles can be transferred to two other particles that have never interacted before.
Entanglement swapping.
Yeah, it's a bit like a quantum game of telephone,
Okay.
where the entanglement is passed along a chain of particles. Imagine having two pairs of entangled particles, A, B, and CD. By performing a specific measurement on particles B and C, we can create entanglement between particles A and D, even though they've never directly interacted.
Wow, so it's like entanglement is a resource
Yes.
that can be shared
Yes.
and manipulated,
Exactly.
creating these connections between particles that were once totally independent.
And as we delve deeper into the world of multi-particle entanglement, we're discovering new forms of entanglement, new ways to measure and quantify it, and new possibilities for harnessing its power for technologies that could transform our world.
Yeah, it really is remarkable how entanglement is blurring the lines between science fiction and reality. It's like we're living in a world where the impossible is becoming possible.
Right.
And it all stems from this interconnectedness between particles that seems to defy the laws of physics as we know them.
And as we continue to unravel the mysteries of entanglement, we're realizing that it's not just a theoretical curiosity, it's a fundamental aspect of the universe,
Yeah.
with profound implications for our understanding of reality and the potential to revolutionize technology as we know it.
So where do we go from here? What are some of the big unanswered questions about entanglement that scientists are still working on?
One of the biggest challenges is scaling up entanglement to create systems with more and more entangled particles. Imagine a network of hundreds or even thousands of entangled qubits all working together.
Wow.
That's the kind of complexity we need to achieve to build truly powerful quantum
It
computers.
sounds incredibly difficult.
It is. It requires a combination of cutting-edge experimental techniques and sophisticated theoretical frameworks. We need to develop new ways to generate entangled particles with high fidelity, to control their interactions precisely, and to protect them from environmental noise that can destroy the delicate entanglement.
So it's a delicate dance between pushing the boundaries of what's experimentally possible
Yeah.
and developing the theoretical understanding to guide those experiments.
Exactly. And on the theoretical front, we're still grappling with fundamental questions about the nature of entanglement itself.
Like what?
What is the underlying mechanism that connects these particles across vast distances? Is it something that travels through space, or is it a more fundamental property of the universe that transcends our classical notions of space and time?
Yeah, those are some really big questions.
They are questions that could keep physicists and philosophers busy for centuries to come.
For sure. So we started with this idea of two particles linked together, and now we're talking about these vast networks of interconnected quantum states that could revolutionize technology and challenge our understanding of the cosmos.
And it's just the beginning. The field of quantum information science is rapidly evolving, and new discoveries about entanglement are being made all the time. It's an incredibly exciting time to be following this field and to witness the unfolding of what could be a truly transformative era in science and technology.
So what's the one big takeaway for our listeners? What should they keep in mind as they go out into the world with this newfound knowledge of entanglement?
I think the most important message is that entanglement is not just a theoretical curiosity. It's a real phenomenon with profound implications that are already starting to impact our lives. Whether it's the development of quantum computers, the promise of secure quantum communication, or the deeper understanding of the universe that entanglement offers, this concept is shaping the future in ways we're only beginning to comprehend.
So keep your eyes peeled for that word entanglement. You'll be hearing it a lot more in the years to come.
Absolutely. And when you do remember that it represents one of the most mind-boggling and potentially transformative discoveries in the history of science.
Well, on that note, I want to thank you so much for joining us on this incredible journey into the quantum realm. It's been awesome to explore these mind-bending concepts with you, and I hope our listeners are leaving with a sense of wonder and excitement about the possibilities that entanglement holds.
It was my pleasure. I always enjoy sharing the wonders of quantum mechanics with a curious audience.
And to all our listeners out there, thank you for tuning in to Podcast Learn and Fun. We hope you enjoyed the journey of learning. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.